So let's continue. So when you do the tracking, it's not always obvious, as we have seen already with the simple example. We had the ambiguity if you have the same distance to the nearest neighbor. But you have also other problems when you do the tracking. So one thing is, again, the noise, which is always around. You can have limited field of view or depth of field that you can work with. And then is the question how you do your segmentation can have an effect. Motion artifacts. I don't know if you saw it, but in the snow movie, we could see that the snowflakes, which should be kind of round, they turned into ellipsoids, which is a motion artifact. And also when it blurs, the intensity falls, and that is a trouble. And then we have the problem, again, also what you saw with the snowflakes, that the paths are crossed and maybe even overlapping if you have 2D data. Cross path, then you have to decide which is the right path, because otherwise you all of a sudden make a very unrealistic turn in your tracking. And all this, of course, is problem. And then on top of it, you can have the problem that objects appear or disappear. They can kind of, if you have a cell culture, all of a sudden you have new cells or some cells die. If you have the snowflakes, they may go out of the screen and sometimes even come back again. And you need to identify those. And that are practical challenges when you do this tracking. What you also have is the problem of jitter or noise. And as it is Easter now, I introduced my little Easter bunny. Anyway, you have predicted or estimated, expected direction, which is deterministic from your track. But on top of it, you also have some jitter, some uncertainty with some amplitude and some direction. And in the end, your object actually lands somewhere else than you would have expected. This gives you an area of uncertainty. And that is actually also used in tracking algorithms where you have your, say, deterministic or expected direction, and on top of it you have the uncertainty area, which you can get from a covariance matrix, for example. And that can be plugged into your tracking algorithm if you would like to have that. Then you also have some other limitations. You can have limitations based on the flow rate. If it's too fast, you cannot find the next likely point easily. Also the type of the flow. If you have straight flow, then it's easy. If you have very turbulent flow, it's much harder to find. The density of the particles is can be a problem, or so mostly if you have too many particles, it's harder to identify which ones. And if you have appearing or disappearing items, then the question how often it happens, and the jitter that I just mentioned. Another thing that I haven't mentioned in the tracking is particle uniqueness. So, for example, if you have just round small particles, they are almost the same, then you can't use that information. But if you have maybe some size distribution, some shape distribution, you can actually use that also in your tracking as additional information. That, for example, if you find a large and a small item close to each other with about the same distance, then you can use the a priori telling that this one is actually that one because it has the same shape properties. So that is additional information. So every information you have is good to add in your tracking algorithm. So how you can improve? One is actually at acquisition time, and the other one experiment parameters. So one is the acquisition rate, so how often you make your images, and the jitter is actually something that in this case would be, for example, that your camera is not very stable, you have vibrations in the system that can introduce some. Then you have the resolution, and that can also help you to fix density and acceptance rates in your data. During an experiment, of course, you can tune your experiment parameters in a way that they match your acquisition. It's usually a balance. On one side, what the acquisition system can do and what you want to achieve, and then you have to do a match between those. Then you can also look into the particle uniqueness, if it's possible. Not always. And then you can look at also the vibration, how you can control it, to control the jitter, and the mixture, how to fix the density contrast. So there are things you can do on both the camera side and on the experiment side to get the best result. So what we can do, one thing is before doing the experiment is to do some kind of simulation and see if the tracking algorithm actually is doing what it should. This can be an expensive approach, because if you have the model, it's fine. Then you can just run your set the parameters through your model. But if you don't have it, then you have to spend a lot of time building your model to do the simulation. So that is the question: what is easiest to handle? You could also run a couple of experiments, do your own labeling in some way manually, and then afterwards also compare the tracking to that. So there are different approaches how you can get the preliminary test data for your analysis. This is actually not my figures. I don't know how they were done, to be honest. That was my predecessor who did these simulations. Maybe I can do that. Yeah, that's so. I don't. Yeah, so I don't know how straight your tracks are, or how turbulent, but it's yeah. So it's quite straight. Yeah. So that is then in that case something you could play with. So if you have the model or some, say, parameter span for your model, then you can try and see what happens with it. That's sure. And the question is now how the simulations can help us, and you already kind of start getting ideas on that. But in principle, it can give us the parameter space and also even give us a starting point for producing the analysis without doing the preliminary, so without doing experiments, which actually also cost a lot to do and prepare. Maybe the material is scarce, so you don't want to run too many experiments, so then you can run 1,000 simulations and see how it behaves very easily. Yes. Then again, we come to how much is enough. Coming back to the statistical questions, you have to decide what are the criteria for a segmentation or for an acceptance rate. So in some cases, you can see here what different things propagate into. It could be, for example, that a 5% error in the bubble position may result in a less than 5% in the flow field, which is good, so less error in that one. But maybe you get a 20% error in topology, and that doesn't look so good. If you look at the shape or volume, you can see maybe, so these are just hypothetical numbers, but you can see maybe that it propagates into larger errors or smaller errors depending on what kind of error you have in what you detect. And that is something you have to tune depending on what you want to look at and also what you can measure. Then when looking into the nearest neighbor, you can look at a lot of other alternatives. We can look at the bijective requirement that you can compare in principle at a chain of particles with each other and see if they belong to the same track. You can also look at the maximum displacement and see which one is the right one. So it's often the starting point is the tricky part because you have to have a starting track. But after that, you can look at the history and work from the history into a better track. The first one, you never have any good estimate on the direction. Or maybe, yeah, if you have laminar flow, of course, then you know that it should be in a straight way, and that can give you the starting point in that sense. Then you can also include some kind of prior and having expected movements, which I was also showing with the bunny. And that are different approaches, and here you can even adapt this offset every round, and then you can get a better guess on where you have the next one. And yeah, then we can look at tracking the derivative. As I mentioned, we can also use physical models for predicting the next position. And as I said, we can also use the Kalman filters for particle tracking. And what you can do is starting up with the nearest neighbor. It's an easy model, but then you can continue doing multiple hypothesis testing. But the problem is often that you have the shortcomings of merging and splitting particles, that it's not so easy to always find the right track, in particular if they're splitting. And then you need to add more physics into it or some more analysis behavior. The question is also how you should label. So if you have a merging or splitting track, how you should label it in the future. So that is also to decide from experiment to experiment how to handle it. Another way of doing the tracking is if you work with the voxels, is to look at correlation between different images. And one way is to compute the correlation in space, or you can also do it in the Fourier space, and then it's just the Fourier transform of the first image times the complex conjugate of the Fourier transform of the second and inverse transform, and that gives you the position. And looking in 1D, it's easiest. Then you can see we have two signals where we have a center point, and we have one which have glided away a bit. Here is the code how to do it. So it's actually, so I had two Gaussian peaks with some random noise on top of it. And then I do the Fourier transform of the two and compute the multiplication and do the inverse transform back again. And the result is that we have a central peak which has a displacement from 0 by the position that I actually added to this. So these were shifted by 6 points, and actually I get a nice peak at +6. So this one tells nicely how much they are shifted. This can, of course, also be updated in 2D, and another way of doing the correlation is to do it manually in space. So here in this code, what we're doing is actually rolling the image, so shifting the pixels and doing the sum between the two images. And with that, we can produce correlation in space. So here, let's see if I can start it. So here we can see how the 5 is moving around, and at some point we get an intensity maximum, and as you can see here, it appears at this point, which corresponds to the displacement. So it can be done in both space and in Fourier transform, but for images, I believe it's much faster to do it with the Fourier transform. Other metrics, when you compare images, is to use the mean squared error or the root mean squared error. It's also a way. So again, doing the same kind of sweeping as we did with the correlation, and then we can see what happens with that. And here we have least square. We find a minimum at this point. So it's a -4, -2. So it actually makes sense. We have the displacement that we wanted. And in the Fourier space, we can do, let's see, we get here, the point is at 2 - 3. So I believe, did I shift it differently? But anyway, here you can see that we got the two Fourier transforms. The Fourier transform look more or less the same. You can't see much difference, but if we multiply them and inverse transform, then we get this point. And then we can look at also the bone slice registration. So we have this a very small crop from the bone slice, and do the Fourier transform from it. Oh no, this is the first, the smaller region, and that is a long piece of code. In principle, this is just for the animation, actually. So, no, wait. I think it's down here. Yeah, there it is. So here you can see what it looks like when we run through the bone. We already have a nice minimum that tells us about the displacement in this image. No, that's a maximum. Oh, sorry. Color coding is confusing me. Yeah, so that shows also again how to sweep through, and we can run it also with the -15, -15, and see that we have a minimum here in the displacement. So that actually also makes sense. Then we can look at the sand grains, and in this case, we have a larger image. So let's try it with the Fourier transform, and we do the same kind of code as we did before, only that it is now in 2D, and we get the displacement. So it was shifted -20 + 30, and here we have half a pixel shift, which is probably just because of the pixel resolution that we have. So we get a nice maximum caused by these two images. So it's a quite quick approach. The other one has to actually scan through the image very many times, and this one doesn't. It does it quite quick with the n² log n instead. So it's the faster way. So now we have looked into the correlation to see how we have displacements between images, but what we want to do with it is also doing registration. So for example, if you have a patient, these are different radiographs of the same patient during a treatment, and you can see that the people doing the images were not able to position the patient the same way all the time, which is natural. It's not so easy to do. But still, we want to put these images on top of each other in order to be able to compare if there was an improvement from the treatment. So for that, we need to align them and put them on the same frame. And what we need to do is actually having some kind of metric. So we already talked about the mean squared error, for example. And the task of registration is that you have two images and you want to bring them together somehow. And first of all, my hands are not in the right way, so we have to flip. And then after a while, you can optimize it and have them perfectly overlapping. And that is what we're doing here in the registration. And what we need is we need a moving image, we need a transform, we need some kind of interpolator that resamples the image in the new transformed coordinate system, and then you compare the fixed image to what you have done, and that is our feedback, how good the registration is for the moment. This is only one step, so what we also need is to add an optimizer which actually runs through and optimizes the position of the transform. And now we need some images, so we have one fixed and one moving image, and these we now have to transform as the next step. So we have affine transformation, we have the translations, we have scaling, we have shearing, and in some cases we even introduce deformable models. It could be, for example, in the patient case, that the patient has changed shape, lost weight or something, and we need to stretch the patient in order to compare the images afterwards. And then the interpolator is, we have a lot of different options for that. We can do nearest neighbor, which is fast, but we can also do a lot of fancy interpolation schemes, bilinear, bicubic, B-spline, etc., to get the best interpolation for the task. Could be that you even have different choices. Sometimes you go for the nearest neighbor in the beginning because it's quick, and then when you come to the final refinement, you may need to do better interpolation schemes, or maybe for the final result only. And then we need metrics. We have already talked about the mean squared error. We could also look for the structural similarity metric, or we can look at correlation factors to compare how good was the latest movement compared to the fixed image. And finally, we need also the optimizer, where you can have different choices. There are plenty to choose from: gradient descent, Adam, and so on. There are quite many available out there nowadays. This is a field that has evolved radically over the last years with the machine learning, and this is something we can benefit from also in this case. So let's build up a tracker. This one I'm going to implement using TensorFlow. It's not actually the ideal choice, but there are the components are available there for the demonstration. Registration otherwise is something you have packages for doing. So let's first prepare our images. We take this region here, or these two regions. You can see that it's slightly shifted in comparison. And this is the images we are going to work with. And then I need to convert them into TensorFlow tensors, which is this, and also do some matching to make them work. And then we have to implement our transformation function and some kind of loss function. In this case, the loss we use is the mean squared error. So we just compute the difference between fixed and transformed, square it, and compute the average value. And then we have our registration iterations. In this case, I have chosen to work with the Adam optimizer, and the parameters we are optimizing are the rotation and the displacement, Tx and Ty. And here we compute the loss function, so how much is the error for the current iteration. We compute the gradient, which is needed for the optimizer. And then I just store the data because we want to look at it afterwards. And then finally, we do registered image as the affine transformation with the final transform parameters. So that is the loop that is described in principle in this. It's a lot of code, and let's see what it actually does. It takes a little while to run. I think it was 20, 30 seconds to run this one. But anyway, in the end, we can see that we have the original image, T0, T1, and that is the one that should move. And here is the moving track, how it was moving using the mean squared error. And finally, it landed in the end position. Looking at the difference, you can see that in the main field here, there is essentially no difference. And out here, you have more differences. That is because we don't have the image information to fill in. So it's actually just fills in what was in the last edge. So it's you can see that this ribbed pattern here, and that is actually just that it takes the last column and the last row and fills in afterwards. The mean squared error is first quite slow, and then it gets steeper, and at some point it asymptotically levels out. And looking at these iterations, you can see how it moves. Let's see, there it is. In the beginning, it's wiggling a bit because we also have the angle in the optimization, and that is what makes it wiggle in this case. And actually, this animation is one of the reasons why I use TensorFlow, because I could extract the frames during the registration process. That is usually nothing that you get because it's just a waste of space. This one is an alternative. So now what we did, we took just the gray level images, and let's see if I can get that one running. No? Okay. I forgot to, I need to update that one. Anyway, let's just look at this one. As an alternative to the gray level image, we can also segment the image, which is done up here. We take the image and set a threshold, which just identify the dark region. And then we compute the distance transform, and the image that we are going to use in the registration process are these two, where you can see just the distance map of the objects. And that is then used in the registration loop. The registration loop essentially looks the same, so there is not much more to talk about in this one. The only difference is the change is that we have a different input image. What we can see now when this one is optimized is, first of all, the mean squared error has a different shape. And also what you can see is that the track is much more straight, so it's easier to handle for the algorithm with this case. And registration is easy when you have very good objects in the image. If it's more or less flat gray, it's much harder for the algorithm to find it, and it easily lands in local minima. So if you have the problem that the registration doesn't really do what you want, maybe you should look at enhancing relevant features that makes it easier for the algorithm to track. And if we look at the losses now in comparison, we have the gray level image with mean squared error, and we have the distance map. And you can see that the distance map actually converges much faster and giving us the result quicker in that way. So the take-home message is, if your registration doesn't work, try to modify the images that it helps, is one thing. You can change the optimizer, possibly also change what parameters you are doing the registration for. In this case, I added the rotation. It wasn't needed because the images were just translated. So we could actually reduce the parameter set. Some cases you want to do even more. So you can have also the grid adjustments in, and then it's a much more complicated optimization. So depending on your task, you have to choose your tools. Also the optimization algorithm, I used Adam here. You could use some other optimizer and see how well that handles the problem. But it's often the problem that you have local minima, and if you got stuck in those, you are lost. Another thing that you could try is a different metric. Now we tried the mean squared error, but you could also try to work with the SSIM, structure similarity index metric from lecture 3. And that I actually leave to you as a challenge to try on your own if you want to play with it. And now I showed, as I said, with TensorFlow how to do the registration, but in practice there are registration toolkits. So for example, in ITK or simple ITK, there is even a more detailed for registrations called simple elastics or elastics. And these are toolboxes that you usually take for doing registration when you really want to do it. If you want to implement it in ITK, this would be the code. So we have the register image where you have to define or convert your images into the ITK format. Then you do some transform, initialize it, do some casting, and set a lot of parameters for the registration. And finally, you start the registration by execute. And then you do the final transformation. So this is the code you would need to run this registration. And here it's using as a gradient descent algorithm for this registration. And this, of course, also finds the right thing. One difference is that in this implementation, it doesn't fill in the information as I did before, but it only leaves it black. That's another option. I mean, it's anyway kind of a nonsense area. And if you look at the difference between the two original images, this is the difference. And if you look at the registered, you see that there is a little bit of jitter in it, but essentially it's a good fit. What you can also do is looking at local changes between images, and now we are looking into correlation again. And instead of correlating the whole image, we look at patches and compare those to see how the patches are matching. And so what you need to do is first dividing your image into this patch grid, and then you check what is the change or correlation within each of these grids. And that can be used when you want to do digital image correlation or volume correlation. And with that, you can actually get deformation terms out of the images, so you can get deformation fields in your images with that. And with that, we can also get quantify the deformation in terms of strain, which is the displacement, local displacement over the position. And then we can get the strain tensor, which tells, in principle, how you skewed or displaced your object. That is often used in material science applications. We want to actually load a sample and see how things locally are displaced. And That is something that is used in combination also with measurement techniques like engineering diffraction, which can measure this from a physical point of view in different construction materials. But can be used also just in general. It's also used in geology. If you have, again, a load cell, which is, I'm going to show an example on the next slide, I think. So what kind of strain you have the volumetric strain, and you have deviatoric strain. And in principle, as the change, the volumetric is a change of scale, and the other one is change of local deformation of the object. And here is an example that was done by my colleague Steve Hall. He had some kind of sandstone, which had some notches mounted, and then he loaded it, and he could identify, with the help of these methods, he could identify a shear band in the volume caused by this loading, and afterwards he could also identify how the flow was changed due to this shear band. So this is something that was done with the help of digital volume correlation. So the last part, the part I skipped last week, is something completely different. Is more, say, presentation part, how you want to bring out your message. And in the end, once you have done all your images or plots or whatever you want to show, you need to prepare it in a good way. And depending on how you want to present it, with who you want to present it, you have to do it in different ways. So, for example, if you have a discussion with your colleague or your supervisor, then you can have a pretty technical, low-level information in the plots. If you're doing a presentation, you have to assume less from your audience, and therefore you need to make much clearer plots. Also for publications, you need to be even more clear, same as for web pages. So the target of your plot must be a design criteria for what you show and how much information you present. And there are quite many ways of doing visualization, and it's not easy to visualize high-dimensional data. And a table, sometimes a table is good, but it's often hard to interpret a table and see trends in it. 3D visualizations, they're nice, they're very beautiful to look at, but if you want to compare them, you have to do a qualitative visual comparison, and that's maybe not always so easy. And sometimes it's also difficult to really highlight the changes you want to see and find problems. So, first of all, looking into the purpose of your visualization, there are two different reasons. One is to understand and explore yourself. Then the audience is very small, very well defined, and the audience also knows pretty well what you're looking at or what the information is. The other one is presenting your results to someone, and then it's often a much wider audience and unknown. You usually don't know really who's sitting in the room when you present something. There could be also the reader of a paper or audience when you give a talk. And at best, you can assume that they have a general understanding of what you're talking about. So that in that case, you really need to guide the viewer in order to give it the best experience. Then this cartoon here gives you a little bit an idea. So if you have a live presentation versus a written document or an email, Then you have the difference is that if you do a live presentation, you are standing there, you can actually also interact with the audience, and that makes the amount of control is high, but you don't need so much level of detail in your presentation. On the other hand, if you write something, you have very low control over how the person are interpreting the information. But on the other hand, in that case, you need high level of detail, or the right level of detail actually, not to make it too cluttered. Actually a quite nice book, this by Knaflick. Then is the question how you present your graphs. And there are very many bad graphs out there. And there are quite many that kind of say, my data is very complicated. You don't understand it. Or the other one is, I really know how to use toolbox XYZ in Python, MATLAB, Mathematica, or whatever. I'm the master of it. I want to show my brilliance. That's also not needed. Also, what you can assume is that most programs make poor plots out of the box. You always need to tweak them somehow. And if you want to make a good plot, you have to spend time on it. There's no way around. And this is something that's actually captured here, the PowerPoint MS Paint era. There was a shift in the mid-90s that in the publications that before that, it was often trained people who did the graphs and did nice graphs. And then at some point when Word and the Office packages came, people were all of a sudden set to make the plots and graphs themselves. And that was a disaster. You probably have seen the smooth line feature in Excel, which is horrible. It's just a spline between the data points, and never use it, please, don't. There are much better ways of doing it. I actually avoid Excel for doing my plots. Excel is good for doing tables, but plots, no. So anyway, keep that in mind when you prepare your plots, that be critical what you actually provide. So here are some bad examples. For example, this one, you're supposed to see that there are some dots within this point cloud, but you don't, because they didn't play with the transparency in the right way, so they are not able to highlight the right information. This one, yeah, you may see that there are some separated trends in this area and this area, but this, no clue. So what you need to do in that case is maybe that you have trend lines and instead have error bands showing how the different things are overlapping. And still, I would say this is probably 6, 7 different plots together. It's too much. So please reduce the amount of data. That one, well, some kind of network graph. That one is maybe possible to interpret, but that is completely impossible. And all this has been presented in papers or in presentations on different occasions. So please don't do things like this. So how to improve this is you have some steps. First of all, what is my message? What do I want actually people to learn from my plot or my drawing? Then next one, is it clearly communicated? Can someone actually get the message you want to tell them? And finally, is it really necessary to have the plot? You have to ask yourself that one too. Mostly it is, but sometimes a plot is not necessary or a figure is not necessary because you have written about it sufficiently, or there are other ones that already show it, and this one may be redundant. So that is also what you may have to ask yourself. A couple of books on this if you want to dig deeper. Again, there is the Knaflic book, and there are many more books about how to present data in a good way. So some simple rules. Never use 3D graphics like the one here. That's even the worst, where you have these cones. What is the cone representing? Is it the height only, or is it the volume of the cone? You never know. But I assume in this case they are talking about the height, but it's a strange way of visualizing it. Pie charts can only be used if you have 100%, or you're talking about fractions, and still they can be a bit hard to interpret. And also the background color, keep it white or transparent, not light gray. That lowers the contrast. And also use color palettes, which actually are adapted to human visual sensitivity. Think about colorblind people, and then use colors in combination with transparency in a smart way. With that, you can get quite far with your presentation. Then you can think of graphics as a kind of grammar. So there, in languages, there are rules how you put things together, and that can actually also, in some theories here, be applied to graphics. So you can see expressing the graphics as sentences and the elements as words, and they can be composed in different ways. And some example, you just, in some software, just do plot, and then you get something. But, and then you get the out-of-the-box result. What instead you can do is thinking about the different components in different steps. So you have the data where you map some variables. You have points. So now I'm not talking about the data points, but actually the glyphs producing these points. Then you need to add axes and coordinates. Here is also important to include that you should have the axis labels. Just blindly doesn't bring anything. With images, it's also always good to have a scale bar and a color bar on the side. And then you need all the labels and annotations around it. And with that, we can get this nice plot in the end. And here I even separated the data into different colors, so you can see that it's below or above some kind of threshold. And then a lot of this I said already, but don't forget the curve legend, axis labels, figure title, all that. Figure title depends a bit. If you have multiple plots in the same figure, then you should have it. If you only have a single figure, then it's usually the title is already mentioned in the figure caption, so then you don't need it. And then, of course, you can do color bars, how the colors are mapped. And then you have the scale bar. It's actually also a matplotlib feature or toolbox that you can add, which brings that into your images. And when we come to the color maps, on the first lecture, I showed you a list of many different options of color maps, but I didn't say much more about it. There is even some kind of decision tree here, how to select color maps. This is very small, but in principle, it says it asks you a lot about your data set, and with that, you finally come into the right type of color map. More about this in that paper. But in principle, you have a plus minus, also divergent color maps, you have continuous color maps, and categorical color maps. And depending on what you want to do, each one is the better choice. And, well, we are a little bit on overtime now, but in principle, these are some examples using the ggplot package where you actually work with these grammar things, where you plot the basic data and then you add the points, and you can add also different annotation features. And first plot is just scatter plot. Then you can maybe make some interpretation and help the viewer, adding a trend line, also adding an error band on top of it. And you can maybe do some kind of, this is a different data set actually, so you have some scattered data, and in the middle you have a higher density, but this plot is hard to interpret, so we could do something like this, where you instead do a local histogram like plot, where you can see the trend, and the values here is the count in each region, and giving it a trend line. That it makes it easier to understand this plot. And all the time you have, see here, with ggplot you can add these different features as you like. Yeah, ggplot is a fun package to play with. Personally, I actually prefer using matplotlib. It's more straightforward, but here you can get some nice features in different ways. Another way is you can also do some kind of intensity bands, so ISO lines around. That's another category. And there are quite many different packages, and then I come back to the thing that my plot looks like I can handle this or that toolbox, but in the end you have to choose one and work with it. And on this web page there is a summary on these different different toolboxes, so there you can look into which one fits your purpose. And that brings me to the end. So today we talked about time series analysis in different ways. We did object tracking, experiment planning, registration, a little bit about digital volume correlation, and finally rounded off with visualization. Thank you for today.